So in this lecture, what we're going to do is kind of generalize a little bit what we've been doing. So far what we've been doing is you have some data points that you think perhaps the true behavior as such is a straight line, and we find the straight line. But what about other shapes? What about parabolas? And there's various different other shapes. I'll try and draw some of them here. So what we have here is a more general curve. Now, I might just write here that the MA and MB, now the MA here is just something that's multiplying A, and the MB is something that's multiplying B. I'm using the language of multipliers here. Now the MA and the MB depend on X. So I could write this as A times M sub A of X. And this is just like f of x. It just means it's for us it'll be some formula in x, plus b times m b of x. So you can get way more curves, way more shapes than just straight lines using more complicated functions. So for example, for a line, this would be just x and this would be 1. Okay, so call these functions, and as I said, they're functions of x, the multipliers of a and b. The normal equations, now we won't go through all the analysis that we did with the minimizing the sum of the squared deviations, the sum of the squared, we're not going to find the least squared errors. But if you were to do that analysis again, so in other words, write this down, find expressions for the errors, square them, add them up, differentiate them with respect to A and with respect to B, solve equal to 0, you end up with these two equations. Now these two equations for you won't have to remember them really, but you'll have to form them from here. And I will tell you, I mean, these you could just refer to your notes to this if you wanted, but I'll just show how they actually are formed. Now I won't go through all the analysis, as I said. So what you do is you take the original thing and you look at the multipliers. So the first multiplier would be MA. You multiply everything by MA and then you add up. So you should have MAY add up. A times MA is MA squared and add up. And the A here is a constant. B by MA by MB and take out the constant B and add up. Then also multiply by MB. So multiply everything by MB. So MB by Y, add up. A by MA by MB, add up, taking out the A. And finally, B by MB by MB, MB by MB is MB squared, so it'll be B by MB squared, add up. So take this thing, multiply by MA and add up, and by MB and add up, and these are the normal equations. And the solutions of this will be equations in A and B, will give you the curve that minimizes the sum of the squared errors. That's the curve of best fit of this type to the data. Okay, so let's do some examples of these. So what might be good here is just to give you a rough idea of what these curves look like. So an ax squared plus b looks pretty much like an x squared, but it's shifted upwards by that b. So you're talking something like this shape. So for example, I think the maximum bending moment on a beam of span L has this kind of a shape, although the b would be 0, so not a great example. Ax squared plus bx, now I'm not completely sure what, so this is a quadratic, I think that's equal to 0 at 0, I think that's what it is. So similar to this. And now if A is negative, it'll have an N shape. If A is positive, it'll have this shape. Okay, something like this. And now let's find out where these formulas are coming from. So here, let's look at the multipliers. The multiplier of A is x squared, and the multiplier of B is just 1. It's B by 1. So this corresponds to the multiplier of B is 1. So multiply everything by 1, which of course does nothing, and add up. So add up the y, there it is. Add up ax squared. Now typically you take out the a there as a constant, and 1 by b is just b, add up the b. The other multiplier of a is x squared. So multiply everything by x squared and add up. So x squared times y and add up. Ax squared by x squared. Now x squared by x squared gives you x to the 4 and add up. b by x squared and add up. There you go. So they'll be the normal equations if you're fitting data to this curve. And what if you're fitting data to this curve? Well, let's look at the multipliers. The first one looks like, we'll look at the multiple of b is x, and the multiple of a is x squared. Now note that you don't multiply this by the multiplier of a, you go back to the start. The multiple of a here is x squared. So this, because the multiple of these two equations will be the same. But this one is slightly different. Multiply everything by x, x by y, add up. A by x squared by x, that'll be ax cubed, and add up. And bx by x is bx squared, and add up. But I have a few more. In theory, I could do all manner of things here, but usually there's only so many things that I'll ask. Okay, let's look at another one here. So this a over x plus b, this one I think, okay, let's see what happens. At x equal to 0, you're dividing by a small number, so it'll be very, very big. And then what happens when x gets big, you'll be dividing by a big number. A divided by a big number is very, very small. And you'll just be left with b. So this is something that's initially very, very big for x small and gets closer and closer to b. Something like this shape. So this might be something you might see somewhere. So just to be clear, when x is small, a divided by a small number is very, very big. Plus b, well, big plus b is just big. So you get big. And then when x gets big, a divided by x is very, very small. Small plus b is just b. So this here would be b. Now the multipliers here are a little bit more complicated. So the multiplier of b, actually we'll do first. That one's quite easy, because b is just multiplied by 1. So you get 1 by y and add up, 1 by a over x and add up. We'll do something with this now in a second. And 1 by b and add up is add up the b's. Now what we might just note is what we do with a over x. Now here what I would do, if you're kind of, there's a little bit of algebra that comes in. What I would do here is I'd ask you, what is this thing? Now some of you would say 2 over 3, and that's correct, but it's not really useful for what I want to talk about. This really should be called 2/3. 2 by 1/3. So similar story, a over x is the same as a by 1 over x. So if you're adding up a over x, you're adding up a by 1 over x. And remember, the x is going to be data, so it'll be a times 1 over x1 plus a times 1 over x2 plus a times 1 over x3. You can take out the common factor of a, and you'll have 1 over x1 plus 1 over x2 plus 1 over x3, etc. In other words, add up 1 over x. So the way you'll work this will be a times add up 1 over x, and then plus add up b as normal. You could take out the b and it'd be add up 1s, but we won't worry too much about that. Then the other one, what's the other multiplier? Now, you could say, there's two ways of kind of looking at this. One of the ways is you could say that the multiplier of a is the same as dividing by x, because that's what's happening. Essentially, it's the multiplier is a divider, and so if it's divided by x, divide everything by x and add up. So let's see what that looks like. Y divided by x and add up. Now, you might get in a bit of hassle here with a divided by x, a over x divided by x again, but the way it works is it's a divided by x and then divided by x again. So it's a divided by x twice, it's a divided by x squared. We'll come back and look, there's a different way of looking at it. The b one is okay, b divided by x and add up, and where you can take out the common factor of b like we did here. Or the alternative here would be, well, what's actually multiplying a if you have a divided by x is 1 over x. And that probably makes things a little easy in some ways. You've got 1 over x times y. Okay, maybe you're in a spot of bother there. But 1 over x times y is just going to be y over x and add up. But it'll make the next one a bit easier. A over x by 1 over x. How do you multiply fractions together? Top, top, bottom, bottom. A by 1 is a, x by x is x squared. Add up a over x squared. Similar story on this last one. Now we'll just look, there's a slight difference between these two in terms of what does the curve do. And there's nothing stopping me going to x cubes or anything like that here. So again, when x is small, So this, when x is small, this is small, so I can forget about that. And then a divided by small is big, so it's going to be big initially. And then what happens when x is big? Well, the a divided by x, a divided by a big number is very, very small, but b times a big number is big. So it's small plus big, which is big. So this is going to be, for small x, it's going to be big, then it's going to get a bit smaller. But then what's going to happen is, as this gets small, this starts getting big. So you get this shape. Now it's not like a parabola, because this kind of becomes a straight line. That I haven't quite captured that, but it does. And this gets kind of infinitely big for x getting close to 0, which isn't quite what a parabola does. Now here we'll just write down the multipliers. The multiplier of this one is multiplier of b is x. So you get x by y and add up. Now a divided by x multiplied by x. So multiplying by x undoes dividing by x. You're just left with a and add up. And then b by x again is bx squared and add up. And the other one, well, if you're going to see what's the multiplier of a, you can either think of it as dividing by x. That's probably the easy one here. Or else you can think of it as this one. But I think actually divided by x works nicely here. Or this one. Divided by x works nice because y divided by x, add up. A divided by x once and then again is a divided by x squared. And bx divided by x is just b and add up. Okay. Now, similar story, you can do this with data. So this would be, I think, you have two things that you control and one thing you measure, usually. So it's like three-dimensional data. You can fit curves like this as well. It works in kind of the same way. Like you have the multiplier of, now I don't think this is actually really going to be examinable, but it just works the same way. So here, this is the multiplier of c is 1. This one I think is the multiplier of a is x. And this one, the multiplier of b is y. So it works the same way. Now the other thing, just a little, so that's how this is going to work in practice. You're definitely not going to go through the full analysis of, you know, differentiating with respect to a and b. We're not going to be doing that. This is how we're going to do it in practice. Now one thing that's going to be useful is you're going to be solving simultaneous equations. Now there's going to be occasions where the simultaneous equations are not going to be very, very nice. Like for example here, if the x and y is data, and like it could have decimals and everything, these things could be very, very nasty. So you got really, really messy, you've got simultaneous equations with decimals. If you have simultaneous equations with decimals, I recommend you use Cramer's rule. Now you have done Cramer's rule last semester, mostly for 3 by 3, but let's do a bit of, it'll just be 2 by 2 here, and we'll just do some revision. So basically you have simultaneous equations and really you're thinking with nasty decimals. Or else the other thing is you could say if you only wanted one of the variables, that might happen. So what you can do is you can write this as a matrix equation, and then if you remember your Cramer's rule, so the way I write it is for here be dx over d and dy over d. D is the determinant of this, and that's on the bottom of both of them, and dx, what you do is you replace the x coefficients, the multiples of x, with the constants. And for dy, you replace the y coefficients with the constants. And I don't know if I have an example here. Hopefully I do. Yeah, I have an example just to remind you what do these bars mean. Well, these are numbers. You right down diagonal minus left down diagonal. Yeah. So it's good if you have decimals. You can do it with more than 2 variables, but we don't actually need it. Right. So let's do an example. So use Cramer's. So here you can see it's very, very messy. Like, I mean, how would you solve this? There's various different ways, but you're probably introducing all kinds of rounding error and everything. It's just nasty. Use Cramer's rule. Okay. So x is equal to dx over d. So d is the easy thing. It's just the coefficients here. Now be careful. The minus is included. Maybe I wouldn't recommend always writing this, but maybe just to make it explicit, it's 0.431 minus 1.21. 10.9, 9.89 times xy, oh I'm running out of space, equals these constants. I'm just going to go to one significant figure, but I'll use these obviously. 0.01. Sorry. Just so you can see, so D is the determinant of this. So 0.431 minus, be careful with the minuses, 10.9, 9.89. Now you can do it however you want. This is just a recommendation. Now for dx, you replace the x coefficients, that's these ones, with, well, these ones. And then the others stay as they were, minus 1.21, 9.89. And you do right down diagonal that by that, minus that by that. So let's see how we go. So I get 8.08 by 9.89, right down diagonal, minus left down diagonal. Now I got a minus minus, so I'm just going to do plus here. 1.21 by 0.0128. Now I'll use 5 significant figures here, maybe. 79.927. Just to be clear on the significant figures. So significant figures, if I say I'm going to use 5, count out 1, 2, 3, 4, and then the last one round if necessary. Now this next one is 6, so I should round this to 7. Divided by this number. You possibly could put all of this in one go, which would be more accurate. Yeah, like I'm going to write that there, but I'm going to actually say, okay, divided by answer, so that'll be there on top, and then the bottom 0.431 by 9.89, right down diagonal, minus, again I got minus minus, which is plus, 1.21 times 10.9. And so I'm actually skipping this bit. So altogether to 5 significant figures, 4.579. That should be enough. So you do 4 and then one more. 9. Does it round? No. Okay. And now similar story for y. I suppose one of the things is I could have kept the bottom of this. I suppose I do have it here, because this is, the bottom is going to be the same, so maybe it does make sense actually to record the two of them here, because you can use that figure again. But off we go. So the bottom we just know, I have it in the calculator, it's the same as this, but the top dy, replace the y coefficients with the constants. So the x's are the same, 0.431, 10.9, replace the y's with the constants. And this will be to 5 significant figures. So I'm going to keep the thing on the bottom here. And I'm just going to change the thing on the top. So right down diagonal, 0.431 multiplied by 0.0128 minus left hand diagonal 8.08 times 10.9. And to 5 significant figures. So I write 4 figures, 5.0 minus 5.046, and then the next one is 3. Should it be rounded up? No. So that's your Cramer's rule that I'll be recommending you use if the numbers are kind of nasty.